gonna record our session here. And let's see. You can only see the bottom. Is this the only part of it I need to see?
It is. 14 and 15, yeah.
Okay. Use your graphing calculator to determine the following details. Now, you have a Inspire, right?
Mm-hmm. So I just plugged all that
Go ahead
in.
and graph that. I could do it on screen, but unfortunately my screen will show the zeros, but they won't show the maxes and the mins, whereas your calculator will. I'm going to go ahead and graph it on Wolfram Alpha at the same time, just so we'll have something we're both looking at that is similar. And let's see, what was this function? 2x to the fourth minus 5x cubed. 2x to the fourth minus 5x cubed plus 2x plus 1 plus 2x plus 1. Did you get something that looked similar to that?
Yeah.
Okay. And you can definitely notice the difference between zooming in and zooming out, right? That is the beauty of Wolfram Alpha, is it shows you up close, and it also shows you when you zoom out, you don't see any of these local relative extrema here. But when you zoom in, where are they? Where's the local maximum?
When you zoom in?
In other words, when I look at this top picture here.
It's right, like, it's at 0.0, or it's at 0.414, comma 153.
Good. And where's a minimum?
1.8, comma negative 3.56.
Okay, let's see if it shows me my maximums and minimums here. No, it doesn't. Yes, it does. There it is. Local max, x equal 0.41, just like you said, and local min, x equal 1.8, 1.7976. Okay, and what else did they ask? They asked intervals the function is increasing and intervals where it is decreasing. Now, hold on 1 second if you would. Hello? Good, Jane. I'm in the middle of a session right now. How can I help you? Yes, you are. Nope, that's fine. Correct. I'll see Georgia next week. Bye-bye. Sure. Bye-bye. I apologize, Sam. I hate to do that to anybody, but there's always the possibility that it's somebody canceling their next session, and I want to make sure I take that. I don't want to head off to their house and have them having canceled. So, and that's exactly what that was.
Okay.
So again, I apologize. I try to take as few phone calls as I can. So again, let's look at this thing. If, here, let me draw the rest of it to the left. In other words, this thing is going to do that, right?
Mm-hmm.
And when we zoom out on it, it looks like a basic U. In other words, it doesn't look like it has any of these curves at all.
Uh-huh.
So tell me the interval where, starting from the left, tell me the interval on the x-axis where this function is decreasing.
On the left, isn't it just negative infinity to that minimum? I just lost that graph.
Yes, it is. That minimum, which is minus 0.41.
Yeah.
Oh no, that wasn't that minimum.
Or the negative 0.33 or 0.336 comma 0.543. That one.
You calculated all three of those?
All three of the minimums or the two minimums and one max.
There's a relative minimum right here where my cursor is pointing,
Mm-hmm.
and then there's a relative minimum over here.
Yeah, I have both of those.
Yeah, I'm not sure Wolfram Alpha gave me both of those. Hold on a second. Let me go down to where we put minimum. Notice they didn't give me the second minimum. They gave me only the 1.8. Ah, that's because that's the global minimum. They gave me you understand the difference between absolute minimum and relative minimum.
Mm-hmm.
The one that Wolfram Alpha is giving me here is the absolute minimum.
Mm-hmm.
And yet they do list a local maximum. But oddly enough, they don't list the other local minimum. But you found it on your calculator,
Mm-hmm.
and it's at, you said minus 3 point something?
Or minus 0.336.
Okay.
And then comma.
And where else is the function decreasing? In other words, here, let me rewrite that on here again. So it's decreasing on the interval minus infinity to minus, I'm just going to round it off to 2 decimal places.
Okay.
Where else? In conjunction with?
Isn't it the 0.414 to 0.18? Or the
1.8?
Mm-hmm.
We're looking for where it's decreasing. So those are the two intervals. And it's increasing on what interval?
From negative 0.33 to 0.414. And from 0.18 to, or no, 1.8 to infinity.
Correct. Seem like you have a pretty good handle on increasing and decreasing.
Mm-hmm.
Okay. So, 15. An engineer collects the following data showing the speed of a Ford Taurus and its average miles per gallon. Find a quadratic function of best fit to this data. Now, are you supposed to use your calculator to do this?
Yeah.
You know how to do it?
Don't I just put it into like a spreadsheet and then get the,
Yes.
what is it called?
Put it into the first columns of a spreadsheet.
And then get the quadratic regression?
Exactly.
Okay, let me do that.
And I don't know that it matters which is column, the first column, and which is the second.
Mm-hmm.
I would make the first column the top, the second column the second. In other words, your first column is going to be your speed, your second column is going to be your miles per gallon. And the way that Inspire works is you want to put those as the labels at the top.
Mm-hmm.
Okay?
Okay.
Sounds like you know how to do this pretty good too.
So I got for the regression 0.017 x squared plus 1.93x plus a negative 25.3. I can repeat it if you want me to.
Please do. Yeah.
Okay, so it was a negative 0.017 x squared,
Okay.
1.93x, got that, and then plus negative 25.3.
Don't need the plus sign there.
Mm-hmm.
Minus. So there's our equation. That's the equation of a quadratic that opens down like that.
Mm-hmm.
And you'll notice something else. It's not linear. In other words, one would almost think that the faster you drove, the worse gas mileage you'd get. And that is true between those 2 points.
Mm-hmm.
The faster, when you go from 30 to 55, your gas mileage actually goes up. I'm sorry, it's this part of the parabola. In other words, your gas mileage is going up as you're increasing speed. But above 55 miles an hour, it goes down slightly. And believe it or not, 30 years ago, when there was a huge oil crisis during the Carter administration, you know what their first step nationally was? To
Drive.
reduce the speed limits to 55 everywhere. In other words, the speed limits used to be 75. And when we had a gas shortage, the government dropped them to 55. All 50 states had to drop their maximum speed limits to 55. Why? Because that used fewer gallons of gas. Notice that's where you get the greatest miles per gallon is at 55.
Mm-hmm.
But now that oil is plentiful, they don't care anymore, and they raised all the speed limits back up. Not always to 75, but most states you can probably go 75 somewhere now. In other words, they did away with that minimum restriction of 55 miles an hour, which was really based. It was not based strictly on the shortage of oil. It was based on the shortage of oil plus automobile deaths decreased when you drop the maximum speed limit from 75 to 55.
Mm-hmm.
And I'm sure they increased when they raised it back up again. But there's a lot of advantages to having a 75-mile-an-hour speed limit. You increase productivity. It doesn't take people as long to get somewhere. So there's a lot greater productivity when you have a little faster travel taking place. But this is kind of interesting, the fact that this follows a quadratic regression as opposed to linear. So what else you got?
I just sent you another picture.
Okay.
No, I could have rotated it.
Okay, I can rotate it as long as I can download it. Can't rotate it if it's strictly part of the email. It took a while to rotate. Okay. I assume we want to do these log problems?
Mm-hmm. I'm not entirely how to. So we have to change them from the log form to the exponential form, and I'm not sure how to do that.
Okay. All log questions begin with this concept. If y is equal to some number b to the x power, that's the exponential format.
Yeah.
The only thing you have to remember is logs are exponents. Therefore, if I want to write the logarithmic expression, I know the other side of that equation's got to be x. Now all I have to figure out is where to put the b and where to put the y. Where's the b go? B always goes down there.
Yeah, that's what it's the substance.
Which means the y goes there. So the only thing I need to know to convert these two things is that logs are exponents. That's the one thing you have to always remember. And an example of this would be 8 equals 2 cubed. Give me the logarithmic expression of that.
For what, 8 equals 2 cubed? Isn't that just log, is that log, and then the little 2 times 8 equals 3?
Yes. In other words, the way I would say that is log base 2 of 8, 8 being the argument, equals 3. So this will allow you to go back or forth. And you have to do each one equally. In other words, you got to be able to go from exponential to logarithmic and from logarithmic to exponential. So let's write the exponential form of the second one. This is completely amazing. It must be a part of my vision that saw it. When I gave you this example over here, 8 equals 2 cubed, I was not looking at the problem. 13.
Oh, that's the same one.
It is exactly the same one. In other words, they want you to put that in exponential format, right? So it's the way I do this is when I see a log expression and the log is on the left side, I say it's the number to the far left raised to the power of the number to the far right equals the number in the middle. Now, I don't know why that works for me, but it does. It doesn't work very good if you've got 3 equals log base 2 of 8, which is the same thing, because now I can't use that number on the far left. But usually your logs are always on the left, most of the time. And so as long as your log is on the left side of the equation, this works pretty good for going the other way. In other words, I know that it's 2 to the third power equals 8. Well, what's 17?
Is that 3 to the power of x equals 2?
Correct. And notice that if I gave you that as a problem, let's say I said this, and I said solve that. Notice that you don't have, there's no algebra that allows you to solve it. X is not 1, X isn't 0, X isn't 2, it's some decimal. And we have no idea how to solve that, but the way you solve it is with logs. In other words, if I were to have given you that problem, you would take the log, you would convert it to logarithmic expression, you would get what they've given us in 17, x is equal to the log base 3 of 2. You can get that number out of your Inspire.
Okay.
Always remember, logs are just numbers. That is a number. And it's not a number that you can figure out, usually, without a calculator. But And the older calculators only had 2 log keys, and that was log base 10 and natural log. Whereas your Inspire, you can put in any base you want. Am I correct?
Yeah.
Yeah, in other words, what did you get when you put in log base 3 of...
I got 0.63.
Yeah, and that makes sense. In other words, x can't be 1, because then it would be 3. And so x has to be a little bit less than 1. So that's the purpose of logs, really, is to solve exponential equations, which there is no algebra to solve.
Mm-hmm.
Now, were 13 and 17 the only? No, I see a 14 over here too. I've just blown it up too much. Let me back it up a little bit.
Oh yeah, I think I cut 14 off. Yeah.
Okay, well, we are almost out of time. Should we do 21?
Sure.
Okay. So convert this.
Okay, so is that just the square root of 2 to the power of x equals pi?
Simple as that. Again, if I were to give you that, you wouldn't be able to solve it without converting it to logs.
Mm-hmm.
In other words, you take your exponential expression, you convert it to that, and believe it or not, that is just a number. There is no variable there. You can put that into your Inspire and it'll give you a number.
I got I got 3.3 for that.
Yeah, if you squared the square root of 2, you'd get 2. And since we got to get all the way up to 3.14, yeah, that answer makes sense. 3.3.
Mm-hmm.
Okay. Let's see, what else? Can I scroll down here at all?
I think I just had those 3 on it. Oh no, you had log 1.
I got log base 2 of 1. You know how to get that exact value, correct?
It says without using a calculator.
Oh, really? Ah, okay.
Yeah.
Let's go over a few rules about that. First of all, the log base anything of 1 is always equal to 0. Always. In other words, the log base 17 of 1 is equal to 0. And why is that? It's because b to the 0 power is always equal to 1 no matter what b is.
So is that then 2 to the power of 0 equals 1, so 1 is 1?
Uh-huh. So the exact value is 1.
Oh, okay.
Because anything to the power of 0 is equal to 1. Including, believe it or not, 0 to the 0 power. That's also equal to 1. But x to the 0 power is equal to 1, no matter what x is.
So then for 26, which is the log base 8 of 8, is that just 1?
Hmm? No? Oh, yeah. Yeah, that's 1, exactly. In other words,
Okay.
when you convert it to exponential, you get 8 to the 1 power equals 8.
Mm-hmm. Okay.
Can you read some of those others? Well, actually, I'm going to let you go. It's after 5.
Oh, okay.
But I think you got a good firm grasp on these. And just these rules that I've talked about with logs, just remember those and you'll be fine with logs. Now, there are some other log rules you'll have to memorize. But you've covered the hardest part, really, I think, today.
All right.
Sam, I will talk to you next time.
Thank you.
You're welcome.
Bye.
Bye-bye.